Welcome to this section on the course on Introduction to Measure Theory, and this section is titled Measurable Sets and Lebesgue Measure. In this section, we shall restrict Lebesgue outer measure to a class of subsets of PR, the power set of R, so that it becomes countably additive. First, we define a Lebesgue measurable set. A set E of real numbers is called Lebesgue measurable if outer measure of A is equal to outer measure of A intersection E plus outer measure of A intersection E complement for every subset A of R. However, in view of subadditivity of outer measure, the inequality M star A is less or equal to M star A intersection E plus M star A intersection E complement is always true. Therefore, it is enough if we establish M star A is greater than or equal to M star A intersection E plus M star A intersection E complement for measurability of E. We name the class of all Lebesgue measurable sets cursive M, and we define the set function small m on cursive M by small m of E is equal to M star of E for every member E in cursive M, and this set function is called the Lebesgue measure. From the definition of Lebesgue measure and Lebesgue measurable sets, these facts are obvious. If E is a member of cursive M, then so is E complement. The empty set and the set R are members of cursive M, and if outer measure of E is 0, then E is a member of cursive M. And finally, countable sets are measurable, which follows from the previous statement. Our aim is to show that the class cursive M of all Lebesgue measurable sets is a sigma algebra. To that end, first we prove this proposition. If E1 and E2 are measurable, then E1 union E2 is also measurable. The brief proof of this follows like this. Suppose we take a subset A of R and note this set identity, and then apply subadditivity on this to obtain M star of A intersection E1 union E2 less than or equal to M star of A intersection E1 plus M star of A intersection E1 complement intersection E2. If I add M star A intersection E1 complement intersection E2 complement on both sides and use measurability of E1 and E2, then we arrive at M star of A is greater than or equal to M star A intersection E1 union E2 plus M star A intersection E1 union E2 complement, and this shows that E1 union E2 is measurable. Thus, we conclude that cursive M, the class of all Lebesgue measurable sets, is a sigma algebra. This theorem we can extend to finite union of measurable sets. In fact, we can extend it to a countable union of measurable sets. That can be achieved by proving this lemma. This lemma says if E1, E2 up to En are disjoint measurable sets, then for any subset A of R, we have M star A intersection union of EI is equal to sum of M star of A intersection EI. We omit the proof of this lemma, but this can be proved by the use of mathematical induction. Now we prove this proposition, which says if we have a sequence of measurable sets EI and E is the union of all EIs, then E is measurable. Further, if this sequence EI is disjoint, then measure of E is equal to sum of measure of EIs. Here we give a brief proof of the first part. Now the class of measurable sets cursive M is an algebra, and so we can replace the sequence EI by a disjoint sequence Fi having the same union E. Now if I set Kn is equal to the first partial union of the first n sets F1 up to Fn, then obviously Kn are measurable and E complement is contained in Kn complement. Therefore, for any subset A of R, we have M star of A is equal to M star of A intersection Kn plus m star of A intersection Kn complement, and is greater than or equal to m star of A intersection Kn plus m star of A intersection E complement, because this quantity is less or equal to m star of A intersection Kn complement. Now if I employ the previous lemma, then we have m star of A intersection Kn is equal to m star of A intersection union of Fi's, and which is equal to sum of m star of A intersection Fi's. Now if I employ equation 4 in 3, then we find that m star of A is greater than or equal to sum of m star of A intersection Fi plus m star of A intersection E complement. Note that this is a finite sum and the left hand side is independent of n. Therefore, m star of A is greater than or equal to sum of m star of A intersection Fi, the sum goes from I goes from 1 to infinity, plus m star of A intersection E complement, and by countable subdividivity of outer measure, we have this sum is greater than or equal to m star of this union, and this equals to m star A intersection E plus m star A intersection E complement, and this shows that the set E is measurable. We leave the proof of the second part as an exercise, and we observe the following from this theorem. First, M, the class of all measurable subsets of R, is a sigma algebra, and Lebesgue measure is countably additive. Our next time is to prove that all Borel sets are measurable. To that end, first we establish that every open interval is measurable. This proof can be achieved by noting that the interval of the form A infinity, where A is a real number, is measurable, and so its complement minus infinity up to A semi-open closed is also measurable. Now if B is a real number, then we can write the semi-open closed interval minus infinity to B. In fact, the open interval minus infinity to B is equal to union of this semi-open closed intervals, and because these intervals are measurable, therefore the interval minus infinity up to B is measurable. Now if I have an open interval of the form AB, then we can write it as a disjoint intersection of two measurable sets minus infinity up to B and A up to infinity, and therefore this interval is measurable. We use this result to prove that every Borel set is measurable. From the previous result, it is clear that the sigma algebra cursive M of all measurable subsets of R contains all open intervals, but B, the class of all Borel sets, is the smallest sigma algebra containing all the open intervals, and so B must be contained in cursive M. That is, every Borel set is measurable. We complete this section by giving, without proof of course, two important theorems on Lebesgue measure. The first theorem is called continuity of measure. If we have an infinite decreasing sequence of measurable sets En, with measure of E1 is finite, then measure of intersection of Ei's is equal to limit of measure of En. And if we have a subset E of R, then this statements E is measurable. For any epsilon greater than 0, there is an open set O containing E such that m star of O minus E less than epsilon. For any epsilon greater than 0, there is a closed set F containing E such that m star of E minus F less than epsilon. There is a Z in Z delta such that E is contained in Z and m star of Z minus E is equal to 0. And there is a F in F sigma such that E contains F and m star E minus F is 0 are all equivalent. And further, if m star of E is finite, then for any epsilon greater than 0, there is a finite union U of open intervals such that the symmetric difference U minus E has outer measure less than epsilon. and this last statement is also known as Littlewood's first principle. Please try this problem after going through the section carefully. First, why are sets in Z delta and sigma, F sigma are all measurable? Justify. And secondly, so the condition measure of U1 finite in continuity in measure is necessary. Thank you.